Welcome back to Josh Does Math. In this video, we're going to be doing a calculus problem that relates to the tangents of two curves. So here are our two curves. We got y equals x squared plus ax plus b, and y equals cx minus x squared. And our goal is to figure out the values of a, b, and c so that both of these curves have the same tangent at the point 3, 3. So we're looking for the values of a, b, and c. And we can find the value of c pretty easily right here, because we know both of these curves go through the point 3, 3. So we're looking at the second equation right here, and we can solve for c pretty easily. I'm going to plug in 3 for y and 3 for x, because we know that the curve at some point goes through 3, 3. So I plugged in 3 for every x and for every y. And now I'm just going to solve this equation. So I end up with 12 equals 3c, c equals 4. So that's the value of c right there. C is equal to 4. Okay, so that was simple. Well, what other information are we given whenever they tell us that both of these curves have the same tangent at 3, 3? Well, we know that at 3, 3, the derivative of both of these curves has to be equal, because it is equal to that same tangent, that same slope. So I'm going to take the derivative of both of these equations first. So the first equation was y equals x squared plus ax plus b. Second equation is y equals cx minus x squared. I'll take the derivative of each of these, and we're going to set them equal to each other. So for the first equation here, take the derivative of each side, and I get dy over dx is equal to derivative of the first term is just the power rule, derivative of the second term is just the power rule, and then I have a derivative of a constant after that, which is just nothing. So this is what I get. Now with my other equation here, whenever I go to take the derivative of it, I get dy over dx is equal to, first term right here is going to be power rule, so is the other term, power up front, one smaller on the power. And now both of these derivatives right here are going to be equal at the point 3, 3. So I'm going to set them equal to each other. So 2x plus a is going to be equal to c minus 2x. And as we know, c we found out was equal to 4. So I can plug in a 4 for c right here. And now my goal is to solve for a. However, I can't really solve for a because I don't know what x is. But we do know what x is. X is going to be 3. That is the x-coordinate for the point at which both of these curves have the same tangent. So I'm going to plug in 3 for every x, and then I can solve for a. So I get 2 times 3 plus a is equal to 4 minus 2 times 3. 6 plus a is equal to 4 minus 6. 6 plus a is equal to negative 2. A is equal to negative 8. And that was probably the hardest thing that is supposed to be done with this problem here, because solving for c was easy, and solving for b is going to be just as easy. Because where is b up here? Oh, well, it's in our first equation. So we got to look there for b. So here's our first equation. I'm just going to fill in the stuff that we have, which at this point it's a minus 8x plus b. So we're looking for b in this equation. Well, how can I do that? Do I know of any point on the curve I can use? Yeah, the point that we're given, 3, 3. So once again, just like we did for the first curve, I'm going to plug in 3 for every x and plug in 3 for every y. 3 equals 9 minus 8 times 3 plus b. So now I go to simplify this, I get negative 6 is equal to negative 24 plus b. Add 24 to each side, and I end up with 18 is equal to b. So that is the value for a, b, and c in this problem. So as you can see, all I did was took a couple of derivatives and just plugged in 3 for x and y, since that's the point 3, 3 that both of these curves have where their derivatives are equal to each other. So that's all there is to it. Thanks for watching.